Welcome to the session. Greeting of the day. In today's class we are going to talk about the process controllers. In the previous classes we have seen about the various PID controllers and various other digital controllers we have seen, such as microprocessors, microcontrollers, PLCs. Those things we have defined. We know that. And one more process of the process controllers are there that we have to see. And dividing these process controllers into such categories, I have used three words: proportional, integral, derivative. On that, I am using only these proportional controllers only, and then sometimes I am using the combination of proportional and derivative. It is called as a PD controller, simply a PD controller. Sometimes I am using proportional and integral, that is I am naming as a PI controller. Sometimes I want to use together only for the better results: proportional, integral, derivative, that is PID controllers. This one importantly we should note. So maybe a proportional, maybe a integral, maybe a derivative, or maybe a proportional derivative, maybe a proportional integral, maybe a proportional, integral and derivative. Such cases are possible. But what are the three factors we should see now? Proportional we should see, integral we should see, derivative we should see. Then this combination we can make PI, PID, PD. So such combination we should know first what is proportional, integral, derivative. We will do. So the process controllers are P controller, I controller and D controller. What is that? This one we have told this. Depends upon present error. I controller depends upon the past error. D controller predicts the future error based on the current rate of change. How fast it is changing. I want to reach a 50 kilometers per speed and I should run. But at what speed it is reaching that 50 kilometers? In the advertisement, bike advertisement, car advertisement, we have seen reaching 100 km per hour in a second, in 8 seconds. Likewise, the advertisements they are giving. It means how the rate of change to reach the target. 60 km per second. We are reaching 60 kilometers in a second, the rate of change, and then it will maintain. How fast from 0 to that speed we are reaching first. We can able to reach this. This is 50. We can able to reach slowly here and we can go 50 here. This is 50. And this is time. Otherwise, I can able to reach the same 50 like this and I can able to maintain. So this is derivative. I want in immediate and I should go. Not slowly taking process. It is a time and distance based. So this rate of change is important to be maintained to cause previous. We have to see this. So it is based upon future errors of the rate of change. We will see. First I have taken the proportional controllers. The proportional controllers gives an output value that is proportional to the error value with a gain value of Kp, the constant I am adding proportionally. That I am naming is a Kp. Some gain is to be added to reach proportionally. How I need 50 km speed I have to go. I have to walk to the 50 meters distance. From here to here I should walk 50 meters of distance. Then 5 meters per minute I should proportionally start moving. I am planning, I am giving input in a proportional way. I should reach there in 30 minutes. Then what I should do now? I am calculating. Proportionally, I am started. Here I am started, I will reach there in 1 hour. So that is the idea. I am giving, such means the speed I am making a constant, I am giving a gain multiply. So 50 meters are there. So I have to add there the gain functions. The proportional response can be adjusted by multiplying the error by a constant Kp, called as a proportional gain constant. Now we are doing. So what happens? I want to do actuator functions on the same proportional only. So there is an error. What happens? I want to maintain here a temperature of or a speed of 50 rpm per minute, and it is running, the difference is showing as 10 rpm per minute. Here we have to output to be 50. Output to be 50. We need. But set value has been given. Set value has been given as 50. With respect to some disturbances, it is running at 10 rpm. So what is then I have to do? 10, it is running. I have to multiply with a constant Kp. In such a way it will be converted to 50. That's the point. Proportional constant I am adding there. How I am adding? 10 it is running. I am multiplying with a constant, proportional constant of 5, and it is going to become 50 now. So this proportional adding of a constant factor is Kp, constant, proportional. I am naming this as a proportional controller. Just we have used the gain factor only 1. A simplest form, we are specifically using the pneumatic controllers. Output signal is the produced error signal multiplied by the constant gain. Error multiplied by gain. Multiplied by gain. Error into gain is the output. That is a proportional gain we have given. I have a few little bit examples we elaborate for the proportional controllers. This diagram we have seen is a closed loop system where I have given the input of 50 meters I have to cross. Input has been given. A control is there, and the distance a person has to move from one end to another end. And let us consider a location where I have to start from here and I should reach to this half of the point. This is the destination point, which is 50 meters. Which is the 50 meters. Now how I can move? I am proportionately planning. How I am planning? I am planning in such a way I am giving the gain of 0.1. What happens? Accordingly, this input has been given and it will move. So I am coming to this graph. You see, distance versus time. Distance versus time. What happens? I have given 0.5. I have given 0.05 as a constant Kp proportional gain. I have given the graph with respect to time. We have to cover the distance 50 meters. It slowly moves and reaches. It slowly moves and it reaches. I am increasing the gain now. What happens? When I am increasing the gain, it is going to contact here, little bit increases and reaches. I am further increasing this value to 0.2, 0.2 I am doing. What happens? You see, it rapidly increasing speed here. We have reached here itself. And then this 50 meter we are ready. So likewise, when the proportionally we are adding more constant, we reach the point quickly. That is the point. Now I am comparing the same with the walking speed. How fast I am walking? How fast I am walking with respect to time. Now I am walking in 5 meters per second to reach that 50 meter. What happens? Immediately 5 meters per second, slowly I will reach it here, the distance. It will take time slowly and we are reaching. Then in case I am walking in a 10 meters per second or high, what happens? I will reach here itself, this point. There we have reached at that point. Later, it takes more time. This x-axis is belong to time. It takes more time. But when I am walking more speed, proportionally I am planning at 10 meters per second again. Therefore, it walks quickly and reaches the point, and we are slowly there. So likewise, proportional planning to be there. That I am making as a constant Kp. So I am making the constant Kp. So this box is a controlling box. Control process, progressive controller. So now I am taking one more example for the proportional controller. I want to lift the aircraft to lift up to 50 meters. Lift up to 50 meters from one end to the other end. That is my destination point. Now it is rotating at some speed, but my aim is to reach there, and it is reached here. Now the machine is off. What happens? This aircraft is fall down. Therefore, it does not work proportional. We have to proportional planning to be done in the revolution per minute at what speed it is to be there. I have given error to be maintained 0, not in distance forward. What I am doing, I am giving first this 50 meter to be reached there, 50 meter to be reached there. Now I am giving an input and it is crossed about 30 meters. We have reached about 30 meters of distance. What is the error now? Remaining 20 meters to be reached. This 20 meter is an error. This 20 meters is error. Error equal to 20 meters. So how I am calculating those things, you see? 50 meters to be done. I am giving a gain of 2. 50 meters to be done. I am giving a gain of 2. I am rotating at 100 revolution per minute. 15 to 100. Up that some stages it reaches the only 30. Some error is there. So what I am doing, that error is 20 now. Error is 20 because we have already crossed 30. First I have mentioned as 50. Now I have already crossed the 20. But I have to maintain rotating. Not error is 0 because I want to rotate at 100 RPM. Then only it is stable there. It is going and it should stable. It should rotate. Then only that drone will be there. The camera drones will be rotating there. So I want to make again 100 RPM. How I am doing? This 20 multiplied by 5, I am getting 100 RPM again. Again it goes and it somewhere it stopped at 10 meters. Now again 10 into, I am multiplying with one more 10. What happens? Because 10 is the difference, 10 is the error. This 10 is the error. So what happens? I am again calculating and again the 100 RPM comes and it is again pushing somewhere a difference of 1 game. And here again I am multiplying with 100 and getting the 100 RPM. Error is not satisfying. Still the error is there. I am naming this error as a steady state error. a steady state error. I am naming this as a steady state error. A constant error is there in proportional controller. The speed is given, it is operated, it is moved, proportionally we have done, but a small micro level error is there, some fluctuation is there. It is not possible to exact maintenance, is not possible. So we are going for the next method of integral method. How micro level is there? We have to distribute and give input. So see, so this is how the error of steady state error is there. So we have to reach this 50 meters. We have to reach this 50 meters. First we have reached 30, again we have reached 20, again we are reaching 1. So we keep on, we are giving proportionally, but some steady state errors keep on coming. Therefore, it is not stopping. I am concluding here that this proportional controller contains a steady state error. Steady state error. Now I am coming to understand this graphical format. How we are doing. The effect of adding proportional control in the system, what happens? On adding a proportional control in a system, time responses of a system improves. Because when the proportional control is not there, we don't know what we are doing. We don't know what speed we should go to reach there. We don't know at what speed we should walk to reach the 50-meter distance. That is why we randomly started and reaches there. Somehow with respect to time, somehow with respect to distance, somehow with respect to speed, we do something. When we are planning for proportionally, what happens? I should reach the 50 meter. I should reach this 50 meter. I am doing a calculation within this time I should reach 10 meters per second. I have calculated. Immediately 10 meters per second it will increase. Next to 10 meters, next to 10 meters, we will reach here itself. And then we can go. Right? We comparatively see us like this. It is looking. What happens? This red line indicates without P. P is not there. Proportional controls we have not done proportionally, we have not planned. Now I have planned well with the proportional 10 meters per second I have to walk speedily to reach the distant point. So the graph becomes quick with respect to time, it is quick and we have reached the level. My response is this one, 1. So in this graph I have reached here itself instead of going for a long time of 8 seconds. I have reached the same this level at itself here. And also in this graph it is exceeding also. Somehow not planned, I am going very fast, this is the level I need. This is the level I need. But it is exceeding here. This I am calling this point as the overshooting. Are possible. Overshooting or undershooting also possible. Because we should not go more speed, we should not go less speed. We should reach that point. That is, I am naming this as a overshooting should not be there. Now, this is one point. The second one, the characteristics of P, I and D. This is what we have seen. The proportional controller Kp, the constant we have done, will have the effect of reducing the rising time and will reduce it will reduce. But never eliminate the steady state error. This steady state error only we have seen now. It never reduces the steady state error. So that is what we have understood. This steady state errors keep on coming there. So what we can do now? I am adding an integral controller here. In an integral controller, the manipulation equals the integral of the error over time and multiplied with the constant of Ki. The remaining part of the subjects, we will see you in the next session. Thank you.